16 of 11, Probability and Statistics. 11, Fall. Number 12, Variance.
Welcome! If you've noticed the weather outside, the scarlet summer is fading into autumn's golden embrace. You know what that means. It's spooky season. That's right, midterms are upon us. Today, I wanted to offer some guidance to those of you taking a statistics course this lovely fall. Guidance in the form of variance. To help you understand, I'll give you a brief explanation of what variance is and how to think about it through an informal derivation. But first, let's take a look at the formula.
This is the expression for variance, more specifically, sample variance. Here n is the number of points, x bar is the sample mean, and x is the variable. That's all well and good, but what does this formula mean? Where does it come from?
This formula arises from three simple properties. First, the measure should be proportional to the data spread. Second, it should be independent of the mean. And third, it should be independent from the amount of data. As it turns out, these three properties create a very useful measure that does more than just give you a vague idea of how spread apart your data is. For instance, the arisings of the ANOVA test. The ANOVA test is like a hypothesis test, but useful for experiments with more than two conditions. Lots of real-world people use these tests every day for their research. We can explore this more in our next video. For now, let's take a look at how variance arises from these three properties.
Let's first consider property 1, making the measure proportional to the data's spread. To fulfill this requirement, let's consider a system of n balls. Let's call the distance of the first ball x sub 1, the second x sub 2, and so on until the nth ball. We will also say that the central tendency of the data in this case is x bar. The spread of the data is how far each point is from the average. To find it, we will subtract each distance from the average, then add them all together. This can be written as the sum of b sub n minus x bar. The second property is independent from the mean. Our current formula fails to fulfill this requirement. A ball placed before the mean will be negative, but one placed at the same distance after the mean will be positive. To fix this problem, we square our entire formula. Now it is mean independent. A third property is independence from the amount of data. But before we start, let's review the concept of degrees of freedom. Degrees of freedom count each independent direction. In our system, we have n degrees of freedom for n balls. However, by knowing the sample mean, we lose 1 degree of freedom. Now let's get back to our explanation. In our formula, if we increase the number of balls, the result of our formula goes up. To prevent this, we can divide by the number of balls minus 1 for the extra degree of freedom. And voila, we have successfully gotten to the formula for variance. Now let's go over an example. Let's say our data set is 1, 2, 3. The first thing you need to do is find the mean. If you recall the formula for the mean, it is the sum of all the variables over the number of variables. In this case, 1 plus 2 plus 3 over 3. Our next step is to find the spread the same way as before. Here we'll have 1 minus 2, 2 minus 2, and 3 minus 2. Now we square, sum, and divide by n minus 1, giving us a solution of 1.
That is as far as we'll go today. Hopefully that gave you lots of knowledge in this midterm season. Of course, there was a lot we had to breeze over, but this should suffice. If you're interested in learning more about degrees of freedom, check out Why Sample Variance is Divided by n-1 by Eden Au on towardsdatascience.com. If you're more of a visual learner like me, check out the science sciencebuddies.org page on Variance for a similar explanation of today's work. Until then, stay well, ace your test, and I shall see you next time, my trinkets.